Hello everyone, and welcome back to the series on intermediate statistics, and today we're going to be continuing our exploration of parameter estimation theory and introduce two new concepts known as the Fisher information and the efficiency of an estimator. So last time we discussed two important functions. The first is the likelihood function, defined as the product from k is equal to n of the associated probability density functions, which obviously simplifies to just the density function for n is equal to 1, and then the log likelihood function, which is just defined to be equal to the natural log of the likelihood function, and for n is equal to 1, that's just equal to the natural log of the probability density function. So what is our goal with estimation theory? Our goal is to estimate theta with some statistic theta hat. So one can begin to ask or try to quantify the following statements. The more information, then the better, i.e. more reliable theta hat is for theta. Right? So the question is, how do you define more information? Larger the value of n, the better, but maybe a sample size of 50 is good for lambda for exponential, but it's not very good for sigma squared for normal. So we have to have a more adaptive version dependent on theta and theta hat, possibly for the information. And then what do we mean by the better or more reliable estimator for a particular parameter theta? This is where the term efficiency is going to come into the picture. Let's also mention a couple other things about this particular thing, because keep in mind we want to estimate theta with theta hat. So how do you find theta hat? Well, suppose that the partial derivative of the log likelihood function with respect to theta, evaluated at theta is equal to theta hat, is equal to 0. And also let's assume that the second partial derivative of the log likelihood function with respect to theta, evaluated at theta is equal to theta hat, is negative. Then this theta hat value is called maximum likelihood estimator for theta. So maximum likelihood estimation theory allows us to find an estimator just in case you do not have one. And also, if the expectation of this estimator, whether it be an MLE or not, is equal to theta, then theta hat is called an unbiased estimator for theta. And unbiasedness obviously is a good skill to have, or a good characteristic to have for a statistic. Asymptotically unbiased would be the second next best thing in the unbiased world. But are there other characteristics, such as the idea of more information, more efficient, more sufficient, all those types of things, more consistent rather? What about these other adjectives that we could possibly attach to an estimator, and how would we sort of weigh one over the other, right? So let's start off with how to define, or one way to define information about a parameter. So the Fisher information for theta from a sequence of random variables xk, where k ranges from 1 to n, is given by, or is defined by, the following statement. So I n theta is going to be defined to be equal to the opposite of the expectation of partial square L partial theta squared. It's very important to note that the log likelihood function and the likelihood function all have xk in them, and they are random variables. So since it's a random variable, it obviously should have an expectation that it's finite, and obviously this expression should, but not always, exist, and ideally should always be a positive number. More on the theory of Fisher information later. But you should see only theta in this particular expression, not theta hat, not x bar, not xk, not anything. You should only see parameters and numbers. Right? So that's a definition. So let's see if we can build the Fisher information for a particular random variable sequence. So let's assume that x is associated to an exponential lambda distribution. So it would be the likelihood function for its parameter lambda b. So that's going to be equal to the product from k is equal to 1 to n of lambda e to the minus lambda xk, which will be equal to lambda to the power of n times e to the minus lambda sum of xk, where that sum ranges from k is equal to 1 to n. So then the log likelihood function for lambda, given xk, will be equal to n times the natural log of lambda minus lambda times the sum of those xk values. And then we're going to have the partial derivative of L with respect to lambda, for which we're eventually going to call the score function for lambda. And that's going to be equal to what? So that's going to be equal to n divided by lambda minus the sum of xk, where k ranges from 1 to m. And then we can set that equal to 0, solve for lambda to get an MLE for it. But we're not going to do that. We're going to find the Fisher information. So that means we need to find the second derivative of L with respect to lambda, which in this case is the partial derivative with respect to lambda of the score function. And that's going to be equal to what? So that's going to be minus n over lambda squared. That second term doesn't have any lambdas in it, so that's just a constant as far as we are concerned. So from here, the Fisher information for lambda will be equal to what? So that's going to be equal to the negative expectation of the derivative of the score function with respect to lambda. So that's going to be the expectation of n over lambda squared. These are just a bunch of constants, so the expectation of a constant is just itself. So we just have n divided by lambda squared. So that's the Fisher information for lambda. Lambda is the parameter for an exponential distribution. So notice that the limit as n goes to infinity of I n lambda is equal to positive infinity. So what does that mean? So the more sample size, or the larger sample size we have, so the larger n is, the more info we have, about the parameter lambda, right? But keep in mind, if the variance of the exponential distribution is extremely large, then you might need to get a larger sample size in order to get the same exact information about that parameter lambda as you would have to the contrary of having a smaller variance for that exponential distribution. So just keep that in mind. So as already mentioned, we define the score function as the partial derivative of the log likelihood function with respect to the parameter for which we're seeking to estimate. And I'm going to be abbreviating the score function by un theta, where the sample size is of size n. Therefore, u1 theta will just be equal to the partial derivative of the natural log of the probability density function of the variable that has the parameter theta as a part of it. I'm just going to be denoting this by u of theta just to keep a lot of the following proofs simple, but that's what we call the score function. Now what I want to do is just go through several different theorems about the score function. It may seem very weird or useless at first, but it's all going to come together because what you're about to see is that the score function actually contains a lot of the information as well, just like the Fisher's information function also does as well. And that shouldn't be surprising because the Fisher's information is just the negative expectation of the derivative of the score function. So obviously they're connected, but the score function sometimes is a little bit more easier to work with compared to the Fisher information. It doesn't mean that the Fisher information is useless, which you're about to see. But let's just get right into a couple of these important theorems that we want to deal with. So the very first theorem that we want to mention is the following. The expectation of u of theta, so keep in mind u of theta, has all of your variables xk in it, this is actually always equal to 0. Maybe you want to pause this video and sort of explore this on your own because this might seem very strange regardless of what theta is. It's always equal to 0? That might be strange. but it is indeed true. All right, so let's see if we can go ahead and prove this. So what is the expected value of u of theta by definition? So we already know that u of theta is the expectation of the partial derivative with respect to theta of the log likelihood function theta, and keep in mind we're only using sample size equal to 1. So by definition, since this is just a random variable, we can integrate the probability density function of this particular object. So that's going to be equal to, so what is the derivative of the log likelihood function of theta? So that's going to be equal to 1 over x of x times the partial derivative of f with respect to theta, and then we're going to have its probability density function fxx. Agree? But keep in mind this is just equal to that by the chain rule of partial derivatives. Notice that we have a couple things cancel immediately. We have fxx here, fx there, so they're going to cancel, and then we're just going to be left with the integral across the domain of our density function of partial f partial theta dx. Now, keep in mind, as long as this probability density function is well-defined and is nice, we can actually factor out the partial derivative with respect to theta of that particular density function and just write that as fxx dx. Some people also refer to this as the Leibniz rule, Leibniz integral rule, which we learned a while back in single variable calculus. And then we have this particular expression. Remember, f of x is just a probability density function, so this integral is just going to be equal to 1. So this is going to be the partial derivative with respect to theta of the number 1. Obviously, that doesn't have any theta in it, so that's just going to be equal to 0. So we have that the expectation of the score of theta will be equal to 0 for any theta that we have. Kind of awkward, but kind of interesting at the same exact time. So let's look at another one. Now let's look at the second moment of u, right? Because we have that the first moment of u is equal to 0. What about the second moment? Will that also be equal to 0 as well? The answer is obviously no. But we're going to show that this is equal to the Fisher information for theta. And here I'm going to be using I of theta to denote I1. Right. What I want to do for this proof, I'm going to start with the Fisher information and then go backwards to the second moment of u. I think that direction is a little bit more trivial, but you can go the other direction if you want. Just mirror the steps if you want to. Okay. So let's see if we go ahead and can go ahead and prove that. You might even want to try and pause the video to see if you can do it on your own. Right. So I of theta will be equal to what? So I of theta, by definition, is going to be the negative expectation of the partial derivative, second partial of L with respect to theta, which would be equal to the negative expectation of the partial derivative of u with respect to theta. That's, by definition, the score. So this is going to be equal to, again, what? So that's going to be the negative expectation of the partial derivative with respect to theta of, and what do we have here? So u is the derivative of the log likelihood function. So it's going to be 1 over f of x times partial f partial theta. Right? So this is the same exact identity that we used before, right? Because that is all u. So how do we do the derivative of this particular thing? Well, that's obviously going to be a product rule. And that's going to be equal to, so let's write this again, so I theta, so we can have a little bit more room. So the negative expectation of, all right, product rule time. So first derivative second. So first times the derivative of the second. So that's going to be partial f squared partial theta squared. So first derivative second plus the second. So second times the derivative of the first. So the first here is 1 over fx, which is the same as fxx to the power of minus 1. The minus 1 is going to come down, change that plus to a minus, and then the power is going to become minus 2, and then it's going to go back on the bottom. So 1 over fxx, the quantity squared. And then by the chain rule, we need to do the derivative of the inside, so that's going to be partial f partial theta. All right? So we have this particular expression, and what else do we have here? What else do we have here? So we're going to have negative expectation of 1 over fxx partial derivative second with respect to theta. Let's distribute this minus sign, and so that's going to turn that to a plus. So we're going to have plus the expectation of, let's write this as 1 over fxx, the quantity squared, times second partial f, and then second theta squared. Now you should notice that this is the same as 1 over f times partial f partial theta, the quantity squared. So maybe I shouldn't write it like that, because that's not the same thing. Partial f partial theta squared. That's just 1 over f times partial f partial theta, the quantity squared, which is the definition of the score function for theta. So we can write this as, let's just write it again. So minus expectation, 1 over fx, then partial squared f, partial theta squared, and then plus the second moment of u, which we're targeting. So let's deal with this first expectation only, and then we're going to leave that alone. Right? And keep in mind what's on the left-hand side. We have I theta. So this is going to be the negative expectation of what? So it's going to be minus the integral over the domain. And then we're going to have 1 over fxx, and then partial square f partial theta squared. And then we're going to have our density function, dx, plus the second moment of our score function. And then what are we going to have here? So notice that those are going to cancel, and then we can Leibniz rule this again. So this is going to be equal to minus the second partial derivative with respect to theta of the integral from minus infinity to infinity of 1 dx. And then what are we going to have? So actually, no, it's not 1, it's f of x dx. That f is coming from that f here. And this, again, is the Leibniz rule. And this, as usual, is equal to 1, since that's a probability density function. So then we're going to have what left? So this is going to be equal to 0, and then we have I theta equals the second moment. So isn't that actually kind of strange? So the second moment of that is equal to the Fisher information for that. And it's also true for n also. It's also n for n greater than or equal to 1. And we also have that the first moment of the score function was equal to 0. So we've proven these very two interesting, potentially useless, but nonetheless interesting results for the score function. All right. Let me mention 3 more theorems. I won't prove these. I'll leave them for you to sort of practice on. But they are actually quite important as well. So the third says the following. So the expected value of theta hat and the score function for theta actually is equal to the covariance between theta hat and u theta. This one's actually not hard to prove at all. Just use the definition of covariance in terms of the product moment and the product of first moments. But another way you could write the product moment of theta hat and u is actually equal to the expected value of partial theta hat partial theta. And you might be thinking, well, why would I represent the product moment of these two things in terms of the expectation of a derivative? That will become clear in a moment. But one can show that the expectation of the partial derivative of theta hat with respect to theta actually equals 1 plus the partial derivative with respect to theta of the bias of theta hat for theta. Now, obviously, if it's an unbiased estimator, if unbiased, this term is equal to 0, so the expectation partial theta hat partial theta will just be equal to 1. That's not very exciting, but this allows us to construct a series of examples for estimators that are both biased and also unbiased. So these are 5 theorems that you definitely should know when it comes to score functions. Now let's see if we can put all of them together to get something meaningful out of it. Recall from probability theory that the square of the covariance between any 2 random variables, whether they be independent or dependent, is always less than or equal to the product of their 2 variances. Right? Now keep in mind the covariance can range from minus infinity to infinity. When you square it, covariance then becomes from 0 to infinity, and the smallest value that covariance can be is 0. So keep in mind this is always bounded below by 0. But this always creates a lower bound for the product of the variances between x and y for any variables x and y, as long as you know the correlation and or the covariance between them. Right? That's a hint in case you don't know how to prove this particular probability result. But using this, what do we get in terms of theta hat and the score? So this means that the covariance between theta hat and the score function for theta squared will always be less than or equal to the variance for theta hat and the variance for u of theta. Now remember that the variance of u hat is equal to the second moment, so the second moment minus the mean squared. But keep in mind the mean of the score function is just equal to 0, so we're just left with the second moment of e, which we know to be the Fisher information for that particular parameter. Also, we have a representation for the covariance in terms of the bias of the estimate theta hat for theta. So what we have here is that 1 plus the derivative of the bias function of theta hat for theta squared will be less than or equal to the variance of the estimate we're using times the Fisher information I n theta. Provided that I n theta is always a positive number, so let's assume that this is always positive, I can divide both sides by it, and then I have that the variance of theta hat will always be greater than or equal to 1 plus b prime theta hat for theta squared all divided by I n theta. And this is the very important Cramér-Rao inequality. The Cramér-Rao inequality. And what does this say? This means that the variance of your estimator is always bounded below by this thing here, which we call the Cramér-Rao lower bound, CRLB. So the Cramér-Rao lower bound. The Cramér-Rao lower bound for any estimate theta hat for theta, even if theta has is an MLE, even if theta hat is unbiased, even if theta hat is asymptotically unbiased, even if theta hat is biased, the variance of that estimator is always bounded below by this Cramér-Rao lower bound. Right? So that's actually very, very, very important. Right? So if, for example, the bias of theta hat for theta is equal to 0, then this Cramér-Rao inequality actually simplifies to the variance of theta will be always greater than or equal to 1 divided by the Fisher information for that. Agree? And you should be able to verify that I n theta actually can be scaled by the information of one individual provided some constraints. So for example, for the lambda parameter for the exponential random variable, that was equal to n divided by lambda squared. So ideally, as n tends to infinity, I n theta will also tend to infinity, which means that the Cramér-Rao lower bound should ideally tend to 0. But keep in mind, this is not always true. Not always true for all theta hat. Some theta hats it's true, but not all it is. So that means what? that means variance of theta hat is allowed to have a smaller variance, or is allowed to be smaller, let's say, allowed to be smaller if we have more information on the parameter that we're seeking to estimate with theta hat. Right? So let's assume that we have this Cramér-Rao lower bound, and technically speaking, we always do, as long as this theta hat exists and the MLE exists and all of that fun stuff. But let's create a new definition. So an estimator is said to be a minimum variance estimator if the variance of that estimator is equal to the Cramér-Rao lower bound, i.e. 1 plus b prime theta hat theta squared all over in theta. Agree? That is, if it's unbiased, if it's equal to 1 over in theta. So if the variance is equal to the Cramér-Rao lower bound, then we say that the estimator is a minimum variance estimator, because there does not exist any other estimator out there that will have a variance less than it, which we've already proven. So if it is a minimum variance estimator, which we abbreviate by MVE, and if it satisfies the unbiased property, we'll call it a minimum variance unbiased estimator, an MVUE. Then we also introduce one more piece of terminology. An estimator is said to be efficient if it is a minimum variance estimator for that parameter it seeks to estimate. Now, obviously, not all estimators will be efficient. Therefore, there will be a lack of efficiency for a lot of them. So, lack of efficiency. And this is kind of the analog to the bias for an unbiased or biased estimator. And we're going to abbreviate that by LE for theta hat for theta. And this would be equal to the variance of theta hat, minus the Cramér-Rao lower bound. Right, which we technically can see is the variance of theta hat minus 1 plus the derivative of the bias of theta hat for theta all over in theta. And keep in mind, this is always greater than or equal to 0 because it satisfies the Cramér-Rao inequality. Okay. Now keep in mind, it could have bias in it, so be very, very careful. But if it is unbiased, then if unbiased, then it's going to be equal to variance of theta minus 1 over in theta. So that's what we call the lack of efficiency for that estimator. So as an immediate corollary, if theta hat is efficient, then the lack of efficiency for theta hat for theta will be equal to 0. And there is one other case that we can define here. We say that theta hat is asymptotically efficient if the limit, as n goes to infinity, of the lack of efficiency for theta hat for theta, take a guess, is equal to 0. All right, so those are the main components that we have up to this stage. Now let's do a brief example on how to illustrate this. So let's suppose that we have a sequence of independent, identically distributed, normal mu sigma squared random variables. And let's assume that somebody asks you, can you find the maximum likelihood estimator for mu and sigma squared? By this time, you should be able to answer yes, of course. So you might remember that mu hat, MLE, was equal to x bar. And you might also remember that sigma hat squared, MLE, was equal to 1 minus 1 over n times sigma squared. S squared, sorry. Agree? So we have these two estimators. Moreover, we found that the expected value for mu hat, MLE, was equal to mu, meaning it's unbiased. And we also found that the expected value of sigma hat squared, MLE, was equal to 1 minus 1 over n times sigma squared, i.e. it's not unbiased, but it is asymptotically unbiased, since 1 minus 1 over n converges to 1. So we have these two statements. So now our goal is to figure out, are these estimators efficient, asymptotically efficient, or not efficient at all? Well, I guess we can't say it's not efficient at all, since they do hopefully have finite variance associated to them. Right? So let's consider the parameter mu hat MLE. So what is the variance of mu hat MLE? So that's going to be equal to the variance of x bar, which you should be able to prove by now is equal to sigma squared divided by m. So question, is this the smallest variance this mu hat can be across all possible estimators of mu? Because yes, mu hat MLE is an unbiased MLE estimator for mu, but there are other estimators out there and also other unbiased estimators out there. For example, the weighted average of the sample means from this population, assuming that it's infinite size. So what would be the conclusion to this? So is this really the smallest variance that it can be? That is it a minimum variance unbiased MLE estimator for mu? Well, we would have to find, the Fisher information, the score function, and then find the Cramér lower bound for all possible estimators independent of this. So let's see if we can do that. So what is the score function for mu? So the score function for mu is going to be, again, the derivative of the log likelihood function with respect to the parameter that we were seeking to estimate, which in this case is mu. And you might remember that this is just going to be equal to 1 over sigma squared times n times x bar minus mu. And if you don't know where that's coming from, I highly suggest you try to figure that out on your own. So from this, the Fisher information for mu is going to be equal to the negative expectation of the partial derivative with respect to mu of this particular object, which is going to be equal to n x bar all over sigma squared. Keep in mind, x bar is a random variable here, and sigma squared is just a non-zero constant. And then we're going to have minus n mu divided by sigma squared. Again, this is just a number without mu in it, so that vanishes. And then we're just going to have a minus n over sigma squared out of there, which negates with the minus sign in front to just give us n divided by sigma squared. Once we have n over sigma squared, then the Cramér-Rao lower bound will be equal to 1 plus the bias, the derivative of the bias squared. Right? So what is the derivative of the bias? Squared, so that's just going to be equal to 0, all over the Fisher information, n divided by sigma squared. So that's 1 over n over sigma squared, which is just going to be equal to sigma squared, all divided by m. Keep in mind, this is the Cramér-Rao lower bound for all estimators theta hat for mu, in particular ours that we're interested in. And keep in mind, this is equal to the variance of the estimator we're interested in, mu hat MLE. So since the variance of our estimator is equal to the Cramér-Rao lower bound, which is the lowest possible variance for any estimator of theta, that means what? So that means mu hat MLE is a minimum variance estimator for mu, right? And moreover, we can say a lot more than that by now. So that means we have that mu hat MLE is an efficient, unbiased, maximum likelihood estimator for mu. Right? And you could go through the same exact calculation for the variance, but I will tell you that there is a bit of lack of efficiency for sigma hat squared MLE. Firstly, it is not unbiased, therefore the numerator of your Cramér-Rao lower bound is not just 1, it's just 1 plus the derivative squared all over the Fisher information. But I do leave to you as an exercise to try on your own the lack of efficiency for sigma hat squared MLE for sigma squared of normal distribution is going to be equal to 2 sigma to the power of 4 n minus 1 all over n cubed. Now, I leave you to explore on your own, is this an asymptotically efficient estimator? I'll leave that for you. But this is some of the main points that you definitely need to know when it comes to finding the Fisher information and also the efficiency or lack thereof of some estimator for some parameter for which you are interested in estimating. Hope you enjoyed this video, and I'll see you in the next one. Take care.